Hello everybody and welcome back once again. In this video we're looking at question number 9 on our Ontario senior paper from 1968. So let's take a look and see what question 9 has in store for us. Here we go, here's question 9. A general point CD is selected on the circle x squared plus y squared. I don't know why they don't have an r squared. I guess they want to highlight this a squared and b squared. Maybe we're gonna have to do some sort of Pythagorean triangle or something like that, but I would have just left it as r squared, but they probably have a purpose. So we got a general point P and it's on this circle. From P, tangents are drawn to this ellipse. That's why they left the a and the b as they were. So this is another way of writing the ellipse. X squared over a squared plus y squared over b squared is equal to 1, which is the more common way to write an ellipse that I'm familiar with, but this is still an ellipse. And it's got the same semi-major and semi-minor axes and everything like that. Okay, show that no matter where P is selected on the circle, the two tangents from P to the ellipse are always perpendicular. Okay, always perpendicular. So I'm thinking there might be two ways to show this because they're giving us equations here. They got the equation of a circle, equation of ellipse. So we might be meant to do this with sort of analytic geometry. So equations, get the equations of the lines and show that their slopes are negative reciprocals. That's one way to do it. I think that might be the more logical way to do this. But tangent lines, this point P is on a circle. So if you imagine a circle, and you've got point P over here, you've got two lines coming from it, if you know that you've got a right angle, the other places that they intersect on the circle will have to be sort of diametrically opposite. They're going to be on ends of diameters. And so there might be some geometry here. Let's get a closer look at this sort of picture. So I know A and B are going to be the semi-major and semi-minor axes. And both equations here have no x minus stuff or y minus stuff, so they're both centered at 0. We'll say maybe A is here and B is here, and we've got sort of an ellipse going around like this. Okay. And then A squared plus B squared, you get a point sort of up here, you get this nice little rectangle, and this is a point on the circle. And not a bad picture. And you can also see this particular point, its tangent, it makes sort of a rectangle with B and A. So you can see it is going to have a perpendicular here. But for another point, maybe a point down here, they're telling me no matter how I do the tangent lines, that they will have to be right angle, in which case you're going to have a diameter and it's going to necessarily go through the center there. So I'm wondering if there's an argument that can be made there without, specifically finding the tangent points in terms of CD or finding slopes of lines, maybe some sort of symmetry argument, like reflect this point in the diameter, or so the problem here is going to be the ellipse does not reflect nicely. So what I'd like to do is sort of reflect this point in this diameter that I know should be there, but that's because I know what they're asking me to do. I know they're saying no matter where you are on the circle, you get this right angle. So no, I know no matter where you are on the circle, you'll get this diameter. So I'm sort of working from knowing the answer, but this ellipse is not going to reflect nicely. And so I was hoping you'd get sort of like the whole picture and this whole triangle reflects, but it doesn't necessarily. And so it might not work. I mean, you could certainly pick the point here that's directly opposite the other point, get another diameter here, and it's going to have tangent points, but are they necessarily going to be the tangent points or the extensions of the tangent lines that meet the circle. Are we going to get some sort of rectangle or something like that? I don't see that necessarily happening, and if it does, I don't see it happening easily. But on the other hand, we do have a bunch of equations. Okay, so we've got the x squared plus y squared is a squared plus b squared, and we know CD is on the circle, so this gives us some information. C squared plus d squared is a squared plus b squared. And we know our ellipse is the ellipse's equation. So what we could do is maybe say, all right, here's CD. Can we understand what tangent lines need to look like? And there was another question we did earlier. I think it was question 3 on the contest, where we had a parabola and we were talking about tangent lines to the parabola. And I mentioned at the time we could probably do a little calculus, but instead we sort of examined what does it actually mean for a y equals mx plus b to be tangent to the given equation for the parabola. I think we could probably do the same sort of thing here. We could also maybe find some calculus way to do it. But so for that question, it was a parabola and there was a point on that parabola. Well, here I'm trying to find tangent points with a point that's off of my ellipse. So I don't think calculus is necessarily the best way to go. I think instead we might say something like, if y equals mx, they've already got a b, so let's use k. So if this is tangent to our ellipse, b squared x squared plus a squared y squared minus a squared b squared equals 0. So tangent lines, they only ever touch at one point. So we can see there is only one common intersection point. And just like we did in question 3, we can put it into a quadratic. We can talk about the discriminant. And the discriminant will have to be 0 to have only one solution to a quadratic. So we've got an expression for y. Take that, sub it in. So b squared x squared plus a squared mx plus k squared minus a squared b squared needs to be equal to 0. Take it to the next page. It was plus a squared, and then it'll be m squared x squared plus a squared km 2a squared kmx plus a squared k squared. I did expand that correctly, right? Yeah. Minus a squared b squared has got to be equal to 0, and a squared m squared plus b squared plus 2a squared kmx plus a squared, let's say k squared minus b squared. We'll just factor out the a squared there. So that needs to be equal to 0. This needs only one solution. If you could solve it for 2 different values of x, you'd have 2 points where that line hits the ellipse, and that would not be a tangent line. So we'll say, therefore, the discriminant is equal to 0, and we'll just jump straight to the discriminant. So that'll be 4a to the 4th k squared m squared b squared minus 4ac squared. So minus 4 a squared m squared plus b squared a squared k squared minus b squared. And actually, I don't need the square root sign. So this has got to be equal to 0. So first things first, let's divide by 4 and a squared. And then we expand things out. So a squared k squared m squared minus a squared m squared k squared. So those will cancel out. Plus a squared b squared m squared That'll probably be another minus k squared b squared. And then minus a plus b to the 4. That's got to be equal to 0. Those first two ones cancel out. And we can divide the rest by b squared. And we'll get a squared m squared plus b squared minus k squared is equal to 0. And no, I don't think there's anything else we can really do there. Okay, so if mx plus k, y equals mx plus k is a tangent to the ellipse, then it's got to satisfy this expression. So the a and b are already given. We know that about the ellipse. We also are now going to claim, okay, now you know that about tangents. Let's talk specifically about the tangents coming through CD. And that'll tell me more about m and k because they're related. Okay, so if P is on this tangent, then you know D is MC plus K. Fantastic. Now, what are we trying to talk about? If we're going to solve this analytically, we're going to have to talk about slopes of lines. We want to show this the only tangents to the circle through C and D, their two slopes are going to have to be negative reciprocals. So we should probably focus on M. And so let's rearrange this expression to get K, and now I can take this K and plug it in here, not unlike what we plugged in Y a little while ago into the expression. So now a squared m squared plus b squared minus d minus mc squared equals 0, and this should give me a quadratic in terms of m, which should have two solutions, which is good because we're talking about two tangent lines. All right, a m squared plus b squared minus d squared minus, so plus 2cdm minus m squared c squared should be 0. So we'll say a squared minus c squared m squared plus 2cdm plus b squared minus d squared is equal to 0. Okay. Now, we could use the quadratic formula and solve for the values of m in terms of a, b, c, and d. But what I want is I want to show that the slopes are negative reciprocals. So another way to do that is to show that their product is -1. All right, well, you might recall from sort of looking at factored form of a quadratic. I think we did this in another question as well. You can find the roots by looking at your coefficients. And so if I want my two roots, my two slopes, and I want the product of them, I take the constant here and divide it by the constant here. So product of the two tangent slopes must be b squared minus d squared over a squared minus c squared. All right? And this should be -1. But is it? But we don't know A, B, we don't know C, D. We know CD is on the circle. So I think we said at the start, so we know A squared plus B squared is the same as C squared plus D squared. So bring the C squared over to this side, bring the B squared over to this side, and take out a minus sign. So the product of the slopes is b squared minus d squared, and then a squared minus c squared, but a squared minus c squared is just minus b squared minus d squared, and we get -1. So the two tangent slopes are negative reciprocals, And we know what happens when you have negative reciprocals. They are perpendicular. And that's all we were asked to show for 9. Always perpendicular, there we go. So regardless of our choice, because we didn't make any specifications, we didn't say, let's assume C and D are over here or anything like that. We just sort of left them ambiguous. The only thing we used about C and D was that C squared plus D squared equals A squared plus B squared because it's on that circle they gave us. That's it. Okay, so I like this nice little conic section question. That was question number 9. Up next is going to be question number 10. I will see you for that then. Take care.